So let's get to the case studies.
So the other case study that I wanted to show is I'm showing it for a different reason. So this is a steam turbine problem, and this was actually driving a hydrogen compressor, and the hydrogen compressor was having mole weight swings that were going from, when they start up with pure nitrogen to almost pure hydrogen with some heavy tails in it and stuff. And so being able to understand what the compressor's power was a big factor on having to understand the mole weight, right? So you needed both sides of this. When it was clear it was running on hydrogen and you knew the power, you could use some of that data and train a machine learning model to understand this was a condensing steam turbine. You come in with a pressure and temperature of steam, you expand across the turbine, and you come out in the two-phase region of, somewhere between 100% steam and 100% water. And so you're at some quality level in there, right, of steam quality. And that's important for understanding how much energy was extracted by that turbine and being able to compare to the compressor. And in this particular case, with the compressor being variable mole weight, you needed to find your data where, okay, it's clearly the compressor is running on its curve. We know the mole weight, everything's good. We know the power. Then you could train, this is what we did here. You trained a machine learning model that would predict the quality based on the inlet conditions, the wheel pressure or the nozzle pressure, the discharge pressure, discharge temperature. You would train the model. So now it's actually predicting what's the steam quality that you would expect here, right? And then you use that going forward so that you can detect variations. And so when you have that variation versus what you're getting from back calculating again with the power from the compressor versus the wheel pressure, we were able to actually, with those deviations, be able to highlight very clearly that you were starting to foul the steam turbine. And again, you're only able to get the independent variables by doing it this way. You don't want to go and tell somebody, hey, you need to overhaul this steam turbine on a single variable. So this is a good case where using and allowing machine learning algorithms to run, first, and then that feeds into some of the physics algorithms that all feeds into the diagnostics, gives you a lot more independent variables that are able to be used to make a decision than any other thing that we could have done here, right? And at the end of the day, again, for visibility, transparency, understanding what's happening and be able to make that decision as you go in, what exactly is wrong? Am I going to work on the compressor side of this thing, or am I going to work on the steam turbine side of this, right?
And in this case, it was fouling of the turbine.
It was fouling of the steam turbine, right? And so we were able to clearly demonstrate that. And again, having the ability to have these models in the same, platform and where orchestration layers can manage the way they operate is what gives you a lot of power in doing this. And condensing steam turbines in and of themselves are difficult, right? Because you don't really know the exit enthalpy, to not be too fancy, right? But you don't know the exit energy levels coming out of it because it's somewhere inside the steam belt. So this is an example just trying to show that it can go from a little more mundane to a little bit more complicated if it's necessary for that particular application. And we're always big focused on, like this. We see this as condensing steam turbines, right? So power generation, refining, some other applications, hydrothermal applications. We see this as across multiple condensing steam turbines. We really try not to do too, individualized, customized everything, because it takes away from your scalability.